Hi, everyone. Hope you're doing well. Today, we're going to be talking about the metric system, scientific notation, sig figs, and converting. Most of the time, we'll be converting from convert metric and customary units from one to the other. We'll also be using some sig fig rules to solve some problems. And then, of course, you guys will be applying past knowledge, like what you've learned, what you have, I guess, learned over the last few years over the metric system and converting. So hopefully this stuff is a review. Of course, with the metric system, you can kind of think that, it's been around for a while, and we're going to talk about that, matter of fact, in the next slide. So um, give some examples of how the United States uses the metric system, and then why hasn't the United States converted all measurements to the metric system? So take a moment, if you would, and just think about that. Think about an example of when you use the metric system in the United States, and then why do you think we have not solely converted to the metric system? So I'll give you guys about another minute, or not a minute, but few more seconds here. So when you think about the United States using the metric system, I think of swimming. When you swim in meters, track and field as well as in meters, and these are for international events. I also think about when you buy some soda or pop, like Coke and all that, that's in liters. That's definitely the metric system. And then not converting into the metric system just yet. Um, Part of it is going to cost a lot of money to convert into the metric system. And I think a lot of it too is that you're looking at is that we use the metric system when we do any kind of international trade. So we kind of use the two hand in hand. So there's really no need to convert. So because we use them interchangeably, um, and that kind of thing. And as you know, the problem is, right, that the metric system is a little bit easier based on the powers of 10, whereas in the English system, you need to know like how many inches, or how many centimeters are in an inch, how many feet are in a yard, things like that. You have to memorize that. So those are the kind of things that can be kind of troublesome, so to speak. I don't know if the word's troublesome, but they can be kind of, you know, aggravating because you don't know exactly what the conversion factors are. So SI system. So we use the SI system, which is called the metric system, in units because we need a way to communicate various measurements in a helpful way. In other words, before people would just say, like 10 meters or 10 feet, there's a difference between those two. Or if you say 10 inches. So you need to really make sure that we know what unit we're talking about when we're explaining something. It's important to know, are we talking about 10 miles? Those kinds of things. So we have to definitely use, when we use units and metric units, we need to be able to explain what we are discussing. So scientific units have been created to define and regulate measurements. Again, back in the day when we had just like the English system, it changed because whoever was the king at the time, that's like the definition of a foot. Well, if you get a new king, then the definition of foot would change. Same thing with like a yard. A yard would be from the nose of the king to his outstretched hand. Well, that changed depending on who the king was. So we had to come up with some kind of way, back in the day, we had to come up with some kind of way that we could say that this is going to be the defined measurement. And so then that's when the metric system was used. So SI, which is again the metric system, it's the International System of Units. And again, it's based on the quantities of 10. Customary units, these are the older units, and these are units that have been used, that we use as well. So when we talk about units, here's the metric system units. So when we talk about time, the unit is seconds, and then the symbol for that is S. Length is in a meter, and that symbol is M. And then mass is the unit or mass is the quantity, excuse me. The unit is a kilogram. Sometimes you can think of it even as grams. Um, and then the abbreviation is kg, but if we're talking about grams, it would be small g. In physics, we use kilograms, not grams, because we're talking about bigger objects like cars, people. We don't use grams for smaller items like bugs or things like that. And then here's some customary units or the English system. Again, length, we usually use foot. Mass, we use slug, and I know you probably have not heard of a slug, but for mass, which is um, in the English system, slug is about 32 pounds, if that kind of helps. Also, with customary units, we use weight a lot instead of mass. So just kind of a side note with that. And then time is measured, of course, in seconds. So that doesn't matter if we're talking about English or customary units. Time unit is going to be the same. So that's kind of the metric system in a nutshell. I didn't really go into major detail. It is thought that you've been studying the metric system for a few years. So make sure you read through your textbook about the metric system if you have any questions. So let's go on to scientific notation. So I'm going to put a lot of stuff out here to you guys today. So scientific notation is something else that I know that you studied. My boys studied it when they were in elementary school. So I know that you've studied it. I just want to review it and make sure that you understand, because sometimes in physics we'll be using scientific notation, and I want you to be able to recognize it. So scientific notation is a way to express very large or very small numbers. It's based on the powers of 10. So the number has to be, the number has to be between 1 and 10, and then you have times 10 to the power added to it. So like, for example, 25.2 times 10 to the fifth, even though it looks like in some scientific notation because you have that times 10 thing, number, it's not, because this number here has to be between 1 and 10, and it's not. So this is not in scientific notation. So you move the decimal 1 to the left, and now this is in scientific notation. So you want to move the decimal point to the right, that's subtracting from the exponent. And then if you move the decimal point to the left, you're adding, like what we did here. We moved it 1 to the left, so we added to our exponent, and so now it is 10 to the sixth. Here's excuse me, a couple other examples. So scientific notation. So here we have 213 million, and so to rewrite that, because it's a big number, to rewrite that, we're going to move the decimal to the left, and then when we move it to the left, it has to be between 1 and the 2. That's because that makes this number between the 1 and 10, which is what you have to have. Because if we go back to this slide, remember that the number has to be between 1 and 10. So moving the decimal 1, 2, 3, 4, 5, 6, 7, 8. So that would be the 8 places to the left. So our exponent would be 8. Here we have a really small number, and so we're going to have to move our decimal to the right to get it to be in scientific notation. Again, it has to be between these two numbers because it has to be between 1 and 10. So we move it 1, 2, 3, and it's to the right. So therefore, it's going to be a negative number, our next negative exponent. So express in an expanded form. So in other words, if it's written in scientific notation and you want to expand it, then whatever the exponent is, you move it that many spots. So again, we have 5.6. So I want to move it 4, because that's the exponent, 4 to the right, 1, 2, 3, 4. And then the same thing with this really small number. I want to expand it. So it's going to be a negative exponent. So I'm going to move it to the left. And so I'm going to move it 1, 2, 3, 4, 5, because that's the exponent to the left. So again, this is just being able to show big and small numbers in a different way, like I said, with scientific notation. Then we're getting into metric prefixes. So metric prefixes is a way to just have another unit, so to speak. Again, it's a way to rewrite numbers. So some of the most popular ones are kilo, milli, centi, and micro. These are probably the ones we'll use the most. Prefixes correspond to the powers of 10, and I'll show you that down here. Each prefix has a specific name and abbreviation, and the prefixes must or can be used with any basic unit. So here we go. So we have 1 millimeter. Milli is the excuse me, the prefix, and then for milli is 10 to the negative 3. So all three of these is a way to write 1 millimeter. So you could write it out as 1 millimeter or 1 mm, or because milli means 10 to the negative 3, you could put 10 to the negative 3 m, which is 10 to the negative 3 meters. 1 centimeter, or excuse me, 1 centigram is also written as 1 cg, which is 10 to the negative 3 grams. And then 1 kilogram, kilo means 1,000 or 10 to the third. Excuse me, so you can write it as 1 kilometer or 10 to the third meters. And here we have another so here we have another thing here. We have prefixes are combined with a base unit, again, to form another unit. So we have 1.21 gigawatts. So it's not just watts, but now we have another unit called a gigawatt. And if you're familiar with Back to the Future, this is from Back to the Future. And here are some common prefixes. Again, these are the ones that we will use off and on throughout the year: mega, kilo, centi, milli, micro, and nano. You've heard of like megabytes, so that's 10 to the 6 bytes, and bytes is a unit for information. You have kilo, so there's 10 to the third, like I said. Centi is 10 to the negative 2. You have milli, micro, which is 10 to the negative 6, and then a nano, which is 10 to the negative 9th. So these are all in the negatives. And then, of course, these are your positives. And then here we're talking about scientific figures, or sig figs, as it's called. And those of you who took chemistry last year used sig figs. Now we're going to use sig figs on some of our online homework. Any kind of homework that you do where it's paper and pencil and you have to take a picture of it and upload it, I'm not too worried about sig figs in that situation, but I do want you to use sig figs on the online homework. So we're going to talk about sig figs here. So this kind of applying some old knowledge. In other words, excuse me, see what you know, see what you remember. So the quantity 2.67 times 10 to the third, this is actually written in scientific notation. And so how many sig figs are there? So just think about it and answer it to yourself, and then we'll come back to it and see if you were correct. So how many sig figs does this have? So all measurements are approximations and have significant figures. The last digit given for any measurement is the uncertain digit. So that certain digit helps you define how many sig figs you need. So significant figures are the valid digit in the measurement. The number of sig figs depends on the precision of the measuring device. So in other words, you cannot be more precise than your device that you're using to measure. Also, your answers cannot be more precise than your least precise numbers. And so we're going to look at some examples here. Okay, there is a little YouTube video that I want to watch that kind of talks about some of that stuff.
Allegedly. Hey, it's Professor Dave. Let's talk sig figs. He knows a lot about science stuff. Professor Dave explains. Humans have a need to communicate their experiences with one another. How far apart are two cities? When did something happen, and how long before it happens again? This is why we developed units of measurement. Some correlate with natural phenomena, like a day or a year, which are based on the motion of the Earth, but many are arbitrary, like most units of length and mass. about 10,400 or 10,472? We have to be careful not to make an estimate that is more precise than our measuring abilities allow. When we use measuring devices, we only estimate one digit further than the level of precision inherent in the instrument. Here, we could estimate 2.33 centimeters, but not 2.33481. We do not have access to that level of precision. So any measurement will have a certain amount of significant figures, or sig figs, associated with it that display how precise it is. Here are the rules for determining how many sig figs are in a value. 1. Any digit that's not 0 is significant. 2. Zeros in between other non-zero digits are significant. 3. Leading zeros, ones that come before the first non-zero digit, are not significant. And 4. Trailing zeros, the ones that come after the last non-zero digit, are only significant if they are decimal zeros. So 10,000 only has one significant figure, which really means it's about 10,000, not exactly 10,000. If we bring back that same crowd and one more person shows up, can we estimate 10,001? No, because we have only estimated to one sig fig. So anything from 9,500 to 10,499 would round to our estimate of 10,000. When we do calculations, we have to pay attention to the number of sig figs. If we are adding or subtracting, our answer will have as many decimal places as the value with the least number of decimal places. If we are multiplying or dividing, our answer will have as many sig figs as the value with the least number of sig figs. Whatever our answer is, we will have to round up or down at the appropriate digit. 5 or higher means round up, 4 or below means round down. Let's check comprehension.
Okay, so we will, let's see here. All right, so I'm going to continue with this. Let's see. Okay, so if we continue to look at, sorry, I think I'm having technical difficulties here. Okay, so if we continue to look at sig figs and the rules that he mentioned, all non-zeros are significant. So again, looking at these numbers, all these have, this is 3 sig figs, this would be 5, this is 4, this would be 6. All zeros between non-zeros are significant. So this 0 would be significant, these zeros would be significant, all of these zeros would be, and so would these. These are between two non-zero digits. All zeros at the end of a number are significant if there's a decimal. So that zero is significant because it's a decimal 0, like the gentleman said in the video. This decimal makes these 4 significant. This decimal makes these 2 not significant, but this one significant. Because this is like a trailing. These are like placeholders. Same with this. This is a placeholder, but these are significant. All right, so let's go through, kind of have some hard time looking at some of this stuff. So let's go through the next couple slides here. So 23.21 has 4 sig figs. This one again has 2 because this one is like a kind of a placeholder, and it's not, it's right after a decimal, but it's not a trailing after a decimal. Again, it's just a placeholder. Here we only have 1 sig fig. It's like that 10,000 in the video. If we wanted to have 2 sig figs, then it should be written as 80 with a decimal, not a 0, because then that 0 would be significant, but it would just be 80 with a decimal. All right, so going back to recheck, this is something from previously. What do you think? How many sig figs does this one have? We have this one, so we have 1, 2, 3. So I would say 3 sig figs, and that would be correct. What about this one? How many sig figs are here? Would be significant. How many numbers are significant in this one? And I would say, yep, 5. Again, these are after a decimal at the end, like a trailing, so those would be significant. So here's a practice problem. Complete the following calculations using the correct number of sig figs. So here you're adding these numbers, and here we are dividing. And so remember the rules is that you can only be, you're looking at your decimal place. So we only have one decimal place past, so therefore our answer can only have one decimal place. Here we have 2, and here we have 3. Now this is for adding. So my final answer can only have one place past the decimal. So if you look, 10.7 would be the answer. And again, you can only have one place past the decimal. But when you're dividing and multiplying, it's about the total number of sig figs, but it's the least total. So here we have 3 sig figs, and here we have 2 sig figs. So my total number of sig figs is only 2. That's the least. So therefore, my final answer can only have 2. And you can see that this 0 is not significant, but this, here we go, the 5 and the 2 are. Another couple of examples here. We have multiplying these two numbers together. There's 3 sig figs here. There's 2. So my final answer can only have 2. And you can see that the 4 and the 4 are both significant. Those zeros are not. Here we're subtracting. All right, there are no decimals, so you can't have any decimal places. So when you subtract them, you might get, the number that you get is going to be have some other significant figures, but you can only have one because this one only has 1, this one has 2, but your final answer can only have 1 because, again, you cannot be more specific than your least specific, all right, or your least accurate. So that's why this would be just 100. All right, and the last thing I want to talk about today is converting. And so I know there's a lot of stuff out there, but I just wanted to put it all in there in one. This is converting. Here we're converting English into metric. So here we have 15 inches. I want to know how many centimeters that is. Well, there are 2.54 centimeters in an inch. So this right here is my is what I'm going to use as kind of my qualifying numbers. In other words, this is how many centimeters are in an inch. Notice that your inches cancel, and then you're left with centimeters. So we have 38.1 centimeters as our answer. And in this one, there's 3 sig figs. This has 3, so my final answer should also have 3. All right, here we're converting 60 miles an hour to feet. So think about, what do we know? Well, we know that in 1 mile there's 5,280 feet, and then in 1 hour there's 3,600 seconds. So to do this conversion, here we have 60 miles per hour, and on the bottom here I have miles, so that way those would cross out. Here we have feet, so that's what I want because it has to be feet per second. So we're going from English to English in this case. And then I have my hour on top, so to cross out with that hour. And then we have seconds on bottom, so we have feet per second. So then my answer is 88.0 feet per second. Now, if you think about this in terms of sig figs, right, there's only one sig fig here. So technically, if we wanted the answer in sig figs, okay, because this is the answer, but if I wanted in sig figs, then if we want it in sig figs, then I would my answer would only be 80, and that would be it, because that would be, again, only one sig fig. So just kind of keep that in mind, even though the answer is 88. If we only wanted one sig fig, because you can only be as precise as your least precise, then my answer should be 80 and not 88. So here we have a car traveling at 55 miles per hour. How fast is the car traveling in meters per second? So we want to convert from English to metric. So if this is what we're looking at here, again, miles per hour, there is 1609 meters, or right around 1600 meters in a mile, if you're familiar with, track and running the mile. Here we have, so the miles are on bottom, so it could cross out with the miles on top. So here on top we have the 1609 meters. Then we have 3600 seconds on bottom, and the hours will cancel out The other hour here on top and bottom, those would cancel out. So we're left with meters per second, which is the unit we want. Now, again, I wrote my answer. This answer has 4 sig figs, right? 24.58. But if we look at when I'm multiplying here, you can only be as precise as your least precise. So this has 2 sig figs. This has 4. This one has 2. So technically, this can only have 2. So instead of being 24.58, it would be 25 meters per second. We would round up because of the 5/8. So depending on your answer, or your answer depends on what they're wanting. If they want it in terms of sig figs, then the correct answer is 25 and not 24.58. But if they don't worry about sig figs, if they just want the answer, then 24.58 is fine. Here I have another kind of quick video I want to show you that talks about converting and how important it can be.
Remember when NASA lost a spacecraft because it simultaneously used imperial and metric measurements on the same mission? The Mars Climate Orbiter disappeared 15 years ago this month, and here's a very brief recap of exactly what went wrong. The Mars Climate Orbiter launched on December 11, 1998 on a mission to orbit Mars. This first interplanetary weather satellite was designed to gather data on Mars's climate and also serve as a relay station for the Mars Polar Lander, a mission that launched a few weeks later. But you can't just launch a spacecraft towards Mars and trust that it's going to get where it's going. You have to monitor its progress. Many spacecraft have reaction wheels to keep them oriented properly, and navigation teams behind interplanetary spacecraft that constantly monitor the angular momentum and adjust trajectory to make sure it gets exactly where it needs to go. In the case of the Mars Climate Orbiter, monitoring its trajectory and angular momentum involved a few steps. First, data from the spacecraft was transferred to the ground by telemetry. There, it was processed by a software program and stored in an angular momentum desaturation file. That processed data was what scientists used to adjust the trajectory, adjustments that were made by firing the spacecraft's thrusters. Every time the thrusters were fired, the resulting change in velocity was measured twice, once by a software program on the spacecraft and once by a software program on the ground. And here's where the problem comes in. It turned out that the two systems, the processing software on the spacecraft and the software on the ground, were using 2 different units of measurements. The software on the spacecraft measured impulse, or the changes by thrusters, in newton seconds, a commonly accepted metric unit of measurement, while the processing software on the ground used the imperial pound seconds. And it was unfortunately the ground computer's data that scientists used to update the spacecraft's trajectory. And because 1 pound of force is equal to 4.45 newtons, every adjustment was off by a factor of 4.45. For a spacecraft traveling tens of millions of miles to a destination, a number of seemingly small errors really add up. During the Mars Climate Orbiter's 9-month cruise to Mars, 7 errors were introduced into its trajectory that meant that when it reached the red planet, it was 105 miles closer to the Martian surface than expected. This turned out to be an unsurvivably low altitude for its Mars encounter. When the spacecraft fired its main engine for the orbit insertion burn that was designed to put it into an elliptical orbit, nothing happened. NASA lost contact quite abruptly with the spacecraft. So while we know the root cause of just what went wrong, we'll never know exactly what happened to the Mars Climate Orbiter. The loss of the Mars Climate Orbiter, very sadly, happened in space. Leave your spacey questions and comments below, and don't forget to subscribe.
All right, so as you can see, that video shows how crazy sometimes just converting could end up in a $1 million loss. So just think about that. And these are people that get paid hundreds of thousands of dollars, and they couldn't and didn't even were not able to convert correctly and cost millions of dollars. So this is done. My video for today is done, and I know it was a lot to talk about, a lot to kind of come together on, but I wanted to make sure we hit all of this stuff and make sure that I get it to you because it all kind of comes together. I wanted to leave you with this nice little cartoon here at the end, and I thought it was just kind of funny. So here's the play. Go out 10 meters, then cut left 5 meters. And then he's looking at meters. Jason, this is football. Everything in football is measured in yards. look, in order for me to get the ball to you at the right place at the right time, I'm going to need to do a whole bunch of trajectory and motion calculations in my head. Trust me, it's a lot easier using the metric system. I'm telling you, you can't play football with meters. It's weird. Fine, go out 10.936133 yards, then cut left 5.4680665 yards. Tell you what, let's stick with meters. So there you go. Hope you enjoyed. And I will get better at this as time goes on. Be sure to take a look at Canvas and see what's next.